Hello. Today we're going to be solving this problem. We have an urn with 3 green and 4 red balls. We choose 2 balls randomly without replacement. Let A be the event that we have 2 different colored balls in our sample. Part A asks us to describe a possible sample space with equally likely outcomes and the event A in the sample space. And then part B is to compute the probability that the event A will occur. Okay, so why don't you give this problem a shot and pause the video and come back when you're ready to see the solution. Okay, so the important statement here in part A is that we need to have equally likely outcomes. So when I first was thinking about the problem and setting up the sample space, it seems that if you want to care about color, so remember that, the sample space is the set of possible outcomes. So one first idea for a sample space could be, my outcome, I have 2 greens, I could have a green and a red, or I could have 2 reds, right? Those could be the possible outcomes. That would define a sample space. But those are not equally likely outcomes, simply because of the probability here. Just the probability of having 2 greens and 2 reds is clearly different because we have a different number of green and red balls. However, what is equally likely in this problem is that we're choosing 2 balls randomly from the set of 7 balls. So in the sense, if we ignored color, if we became colorblind for a moment, then it seemed like everything would be equally likely because we're choosing 2 balls randomly from a set of 7 balls. Okay, so the key to part A is to ignore the color. Okay, so let's draw our set of balls. And then I'm going to label these balls 1 through 7 and momentarily ignore their color. Okay? So then if I ignore the color, then my sample space, the set of possible outcomes, is just the set of possible choices of 2 balls. So this is going to be equal to the set of, let's denote a set xy such that x and y belong to 1, 2, 4. Okay, so this is perhaps a little bit cumbersome notation, but it gets the job done. So essentially, my sample space is going to be this set of sets, and each outcome in my sample space is of the form x comma y. So it's a set with 2 elements, and this x and this y are essentially the numbers of the 2 balls that I've chosen. Okay, so I'm requiring that I'm choosing the balls without replacement. So I have to ensure that x is not equal to y, and then these 2 numbers encode which 2 balls that I chose. Now notice that I didn't use the notation of a coordinate pair x comma y like this, as I've used in the previous problems. And so there's kind of a distinction here because in this, so the difference is that if I would have written a coordinate pair x comma y like so, then all of a sudden I would actually have some ordering here, where the first coordinate is distinguished from the second coordinate. So this would be like the first ball that I chose and the second ball that I chose. But in this stage, I'm kind of going to assume that I'm choosing the balls at the same time. So I'm basically just reaching into the bag or to the urn and choosing 2 of the balls randomly, and so there's no order on this set. So I just have the kind of a set x and y. Okay. So in particular, like 1, 2, if I had chosen the balls 1, 2, this is the same thing as if I had chosen the balls 2, 1. Whereas in previous problems, our convention was with order, and with order, these are not the same outcome. These are different outcomes with order. Okay, so this is without order. And now to ascribe a probability, well, since I've ignored color, then clearly all of these outcomes are equally likely, because I'm just choosing 2 elements uniformly at random from this set. And so essentially the probability of a single event x comma y is going to be equally likely for all possible outcomes, and the probability of this outcome occurring is simply 1 over the number of total possible outcomes, which is the size of our sample space. Okay, and to determine the size of our sample space, I need to determine the amount of ways that I can choose 2 elements out of a 7-element set without order. And that is precisely 7 choose 2. So the size of this set omega is equal to 7 choose 2. Okay, and this is by definition 7 factorial divided by 2 factorial times 5 factorial. Okay, now if you haven't seen this mathematical choose notation before, let me just quickly justify it for you. So if I have a set consisting of 7 elements, okay, and I choose 2 of these elements without replacement, then I have 7 choices for the first element. And then once I've chosen an element, I only have 6 elements remaining. So I have 6 remaining choices. So that gives me 7 times 6 total possible outcomes. However, I've ignored order. Okay, so I have to account for the fact that x comma y is equal to y comma x. Okay, so in this scenario, I've not accounted for that fact because I've counted 1, 2 separately from 2, 1, for instance, in this counting procedure. So to account for this overcounting, I need to divide by the number of ways to rearrange the set, which is just 2 factorial. But dividing by the 2 factorial allows me to remove the ordering. So removing the ordering essentially by allowing all possible rearrangements of any given choice of elements. And when I remove the ordering, then I get exactly this expression. So notice that this expression is precisely equal to 7 factorial over 2 factorial times 5 factorial. And it's a more general fact that if I have a collection of n objects and I choose k of them, then if I choose them without order, right? If I just grab them from a bag and I don't care about the order of my choice, then there are precisely n choose k ways of doing so, which is by definition n factorial over k factorial times n minus k factorial. Okay? All right, so that motivates this construction. And so now we've determined that the probability of each individual outcome in this sample space is 1 over the cardinality of omega, which is, if I just flip this fraction over here, 2 factorial times 5 factorial over 7 factorial. And then if we want to expand this out, this is 2 over 7 times 6, which is equal to 1 over 21. Okay, So each possible event has a probability of 1 in 21 of occurring. Okay, now let's actually compute probability of A of happening. So this was, we've kind of ignored color till now, and now we're opening our eyes and we see in color now. Okay, so now we need to determine the number of ways that that I can choose one green and one red ball. Remember, the event A, if we return to the original statement of the problem, okay, so recall that A is the event that we have two different colored balls in our sample. Okay, so in this case, if I just labeled the green balls as 1, 2, 3 and the red balls as 4, 5, 6, then I need to determine the number of ways in which I can choose a green ball and a red ball. Okay, so this is actually not too hard. There are 3 ways of choosing a green ball and 4 ways of choosing a red ball. Okay, so let me just keep the all right, so number yeah, so the number of ways to choose a green and a red ball. I have 3 ways of choosing a green ball, and I have 4 ways of choosing a red ball. So there are 12 possible. So there are 12 possible combinations x comma y, where x is green, so x belongs to the set 1, 2, 3, and y is red, so y belongs to the set 4, 5, 6, 7. Okay, so yeah, so just via multiplication alone, I can see that this number is 12. And notice that these are disjoint groups. So choosing a green ball and choosing a red ball, these are like, once I choose a green ball, I'm not decreasing the number of red balls. And so that justifies why I can just multiply these two numbers together in this way. And so, now I know that the event A that I'm trying to find the probability of the event A occurring, the event A has 12 possible outcomes associated to it. Each of those outcomes has a probability of 1 in 21 of occurring. So that tells me that the probability of the event A is simply the size of the set A divided by the size of the set omega. And this is going to be, again, the size of the set A is 12, and the size of the set omega, as we already calculated, is 21. All right, and then we can simplify this fraction as 4/7. Okay, awesome. Thanks for watching.